Hello everyone, welcome to CodeGrad, and today we'll discuss the topic transformers. And transformers is an important component whenever we discuss GenA as multiple LLM models were built on this architecture and were built on this based on this architecture. So we'll start with the transformer. It is a neural network architecture designed to transform an input sequence into an output sequence excelling at understanding context, and it was originally developed for sequence transduction, tasks like neural machine translation. We can also define transformers as a deep learning architecture. It was introduced by Waswani in 2017 in the paper Attention is All You Need, and it's designed for handling sequences like text, code, and speech. And unlike other models, transformers can look at all words at once instead of one at a time. So previously, when we were using RNN, LSTM, or GRU, this architecture for sequential tasks or for textual data, at that time these architectures were sequencing words each one by one. But in case of transformers, we can sequence or work on this word all the work at one time. So this is the advantage of transformers over the previous architecture. Now the shift from RNN to transformers. RNN process data sequentially, making them slow for modern GPUs and prone to losing information over long sequences. So previously, when we were using the RNA, it was very slow for the long textual data, and the modern GPUs were not supporting them. So there was also lot of information lost whenever the long sequences were involved. So this was not preferred for long textual data or the large data set which had the longer sentences. Now, Transform will overcome this issue using parallel processing and the attention mechanism. So, whatever the previous advantages were faced by the RNN and LSTM GRU were solved by using the parallel processing and attention mechanism, which is the transformers architecture. Now, in case of the RNN and LSTM or GRU, the words are it is read by word, but in case of the transformers, it looks all the at full input at once, and in case of the RNN, the it was hard to parallelize, and in case of transformers, we can fully parallelizable. It is fully parallelizable, and in case of the RNN, long term memory is weak, as you have discussed here. Whatever the long term information was there, it was not good because there was a lot of information loss. Whereas in case of the transformers, we can handle long term dependencies, and in case of the RNN, it is a sequential structure, while as in case of the transformer, it is non-sequential with attention. Now, transformers replaced RNNs for most modern NLP tasks like ChatGPT, BERT, or T5. So this is the most important point you can consider. Now, the core, the attention mechanism. Transformers rely almost entirely on attention to analyze relationship between the different elements in the sequence, and this allows the model to focus on relevant parts of the input regardless of their distance. At the heart of the transformer is self-attention, where each word looks at every other word in the sentence. It weighs the importance of other words when processing. For example, we have the sentence "the cat sat on the mat," and the word "sat" might attend more to cat. Now, in case of self-attention, it is context aware and we can parallelize it, and it is also flexible. So these are the core concepts of the attention mechanism. Moving on, we have the overall transformers architecture. Now, it consists of two main parts: the encoder stack and the decoder stack. The encoder processes the input sequence, and the decoder generates the output sequence based on the encoder output. So you can consider it as encoder does the understanding part, while the decoder is the generating part. If I pass any sentence and I want to get an output from it, so first of all, the encoder will understand the input we have passed, and the decoder will generate the output according to our question. Now, in case of encoder, it reads only and encodes the data, while at the decoder it generates output word by word. In encoder, we have multiple layers, while in decoder, it has similar layers, but we have extra layers to the decoder part of the. In encoder, we use self attention, while as in decoder, we use self plus cross attention. Now, the encoder. In case of the encoder, it transforms input tokens, that is the word, into contextualized numerical representation, that is the vector. So, whenever the input tokens are passed, which are the word, they are converted into numerical data, or we can also say it as vector. It captures the context of each token with respect to the entire input sequence. And we can also say that in case of the encoder, it capturing the context of each token is very important, and it basically captures the context with respect to the whole sentence. So if you have an example, the cat sat on the mat, the word cat has all the understanding about all the words in the sentence. So this is the encoder one. First of all, we'll start with the now encoder has multiple steps here. First is the input embedding. Whenever the word is passed to a model, the encoder does the input embedding. So converting the words into textual part, converting the words into the numerical formats called as the embedding, and we can also say it as numerical vectors. So converting input tokens, words or subwords into numerical vectors using embedding layers. We use embedding layers to convert these tokens into numerical vectors. Now, these embeddings capture the semantic meaning of the token. Whatever the embeddings we are creating, it captures the semantic meaning of the token. So, whenever the numerical vectors we get, they actually are related with each other and they do the semantic or the actual meaning of the tokens is what we get. Now, in case of input embedding, we can also define it as that each word will be converted, is turned into vector using an embedding layer, and these vectors capture word meaning. Like if you are comparing two words, cat and dog, so it will capture the semantic meaning of these two words. Now moving on, we have the position encoding. So it adds information about the position of each token in the sequence to the embedding. In case of the RNN or LSM or the this architecture, we were processing each word sequence by sequence. So the order of the what we can say embedding was maintained. But in the case of the transformer architecture, we do not go sequentially. So we add information about the position of each token. In the sequence embedding, we use the position encoding. Now it uses a combination of sine and cosine function to create unique positional vectors. Transformers basically don't know the order by default. So we add position. Example, we have the first, second, or third word. Using sine and cosine function, we take the order and we give the order of the particular token in a particular sentence. And now the model knows that if we have example the cat sat on the mat, so we know the cat comes after cat. So order is maintained by using the positional encoding. Then we have the multi-head type attention. It allows the model to weigh the importance of different words in the input sequence relative to each other. And it does this by calculating attention scores using query key and value vectors derived from the input. Now, this is the core mechanism. We should understand this. Each word looks at all the other words and decide which are relevant and how much to focus on them. And that can be done by the using the attention mechanism. And what is multi-heads? We have multiple views or heads for deeper understanding. Next is the self-attention, that is the head. Now, instead of one attention calculation, the multi-head attention performs several attention calculations in parallel, and each is a head. Now, each head learns from different aspects of the relationship and their outputs are combined for richer representation. Now, each head computes its own attention and they are combined and projected for richer info. Now, think of each head as focusing on a different feature, like one is for syntax, one is for entity. So, by using multi-head, we calculate the overall meaning of each word into the whole sentence. So, this is the self-attention using the head. Then we have the encoder sublayer, second one, that is the feed forward neural network. So, now as per the definition, it processes the output from the multi-head attention layer at each position independently. And it typically consists of two linear transformations with a relay activation in between. Now, after attention mechanism, each word vector goes through a small neural network. It applies non-linearity using the relay activation function and it learns deeper features. And this is done independently for each word. So this is the feed-forward neural network. You can consider it as a neural network which has the relay activation function and it learns deeper features. Now, next we have the residuals and the normalization. As per the definition, the residual connections add the input of a sublayer to its output, helping with managing gradient in deep network. And also, layer normalization is applied after each sublayer attention and forward few neural network to stabilize the training. Now, each sublayer has residual connections. That is the skip connections is another word for that to avoid losing information. So, residual connection we are using after multiple processes. There is a option of losing the information. So, to avoid that, we use the residual to avoid losing information, and we can also call it as the skip connection. And the layer normalization is used for stability, and this helps in the destacking of layers like we have 12 or 96 layers in GPT. Next is the decoder one. Now, in case of the purpose and auto-regulative nature, generates the output sequence token by token based on the encoder output and previously generated token. And it operates in an auto-regulative manner, meaning each step output is fed as input to the next step. So in case of the decoder, previously in case of encoder, we have seen it is used for understanding the text, while for decoder we are generating the text. So it takes the encoder output, whatever the encoder has understood, the output is then passed uh, to the decoder one. In case of the decoder, it takes the encoder output and plus generated tokens so far and processes the next word one by one. That is the auto-regressively. Now this allows the model to generate coherent sentences step by step. So this is the purpose and auto-regressive nature of the decoder. Next we have the sub-layer one, which is the mark multi-head self-attention. Now it is similar to encoder self-attention. We have seen the mark uh, we have seen the multi-head self-attention, but now we are going to see the mark one. Now similar to encoder self-attention, but mark to prevent positions from attending to subsequent future positions. It ensures that the prediction for a token only depends on known output at previous position. It is like encoder self-attention, but it can only look at the previous word, not future word. So masking is basically we are hiding the future context, and by it we can look at only previous record or previous word, and we cannot access the future word. It generally in generalized sense we can say it prevents cheating. The model shouldn't see the answer while generating it. Now for the sublayer 2, we have the encoder-decoder attention, that is the cross attention. Now it allows the decoder to focus on relevant parts of the input sequence and which we get from the encoder, and it query comes from the previous decoder layer while keys and values come from the encoder output. Now this layer allows the decoder to look at the encoder output and decide what parts of the input to focus on. Example in translation, we had the example like the cat side on the mat. The decoder may look at cat when translating ghetto. So this is the cross attention in which we have query vector coming from the decoder while the keys and value vectors are coming from the encoder. Now, whenever the we use cross attention generally when we are translating, like we have to translate from English to Spanish or from Spanish to English, we need to summarize some data. So at this point of time, we use the cross attention. Now, next is the feed forward network. We have seen this earlier. It is identical in structure to the encoder feed forward network applied to each position, but further processes the output from the encoder decoder attention layer. It is same as an encoder. It does the non-linear transformation of each token, and it helps model complex relationships. So this is the purpose of the feed forward network, which was seen earlier. Now the final output generation. The decoder final output passes through a linear layer, that is the classifier and the softmax function. This produces probability scores over the entire vocabulary for the next token in the sequence. Now the final vector for each token is passed through a linear layer, the softmax layer, and it predicts the next word token with probability. Example, we have the 80% chance that it's sat, or a 15% chance we have that it is stood. So naturally it will go for sat. So we do the probability at the end of the generation. Now in case of summary, we'll start with the first one. The input embedding generally turns words into vectors. The second one is the position encoding. We can say it adds order info. Third one is the self-attention. It allows tokens to focus on other. Multi-head, we can say that it does multiple attention views. Then for the feed-forward neural network, we have the deep transformation. For the decoder, which generates output word by word. And for the mark attention, it prevents future picking. For the cross attention, we can say decoder looks at input and the final output is predicts the next one. Now, why transformers are powerful? It is fast and parallel, and it can handle long text. It learns deep relationships and forms the base of the models like BERT, GPT, and T5. So this was the final representation of the topic transformers. Hope you guys understood, and if you did, then please like and subscribe our channel, and we'll see you in the next session. Till then, bye.